Now that you have seen design of output layer, we will simply now move forward to optimize, how do we optimize this particular neuron model. So whenever you want to go for an optimization, first you have to understand what is the error that is coming into your neuron model. So today's topic will be error calculation. Right. So after building the model structure, the next step is to select the appropriate error function to calculate the error. So there are different types of error functions which are available, like mean square error, cross entropy, KL divergence, hinge loss, etc. So amongst them, what we are going to study most is about mean square error function and cross entropy error function, and these are more common in deep learning. So the mean square error function is basically used for regression problem, and cross entropy function is mainly used for classification problem. So this you have to keep in your mind while you are designing your neuron model. So when I talk on mean square error function, so mean square error functions, what it is going to do is it is going to map the output vector and the true vector to 2 points in Cartesian coordinate system, and this is done by calculating Euclidean distance between these 2 points. How do we measure the difference between these two vectors? Very simple. You please understand how do we calculate mean square error. I already taught you. There is always an actual output and there is always a predicted output, right? So this is your actual output which is already present inside the model while you were training it, and this is the predicted output that the model got after receiving a particular input. You are going to find out difference between the two, and then it cannot be negative the error, that's why square it, and then you average it out by using mean. So you have got summation and division by the number of samples to give you mean squared error. If I want to define it properly, then I can say that you are going to calculate Euclidean distance between these 2 points of Cartesian coordinate of the output vector and the true vector. Or if you really want to understand, it is like difference between actual and predicted value squared and then averaged out. So in whichever way you want to recollect, you can, but you make sure you write the mathematical expression clear. Okay. Always remember, MSC value is either 0 or it is greater than 0, it cannot be negative because we are squaring it. So whenever the mean square error function reaches to the minimum value of 0, that means the output is exactly matching with the real output, the predicted output is matching with the real output, that is, we call it true label. And then the parameters of the neural networks, they are perfect now, they are in the optimal state. So you always make sure that your neuron model should get a minimum error or almost 0, minimum almost 0, that's what I am telling. So when you approach that, that means your neuron model has got an optimal state, and you stop there and you say the parameters are also optimum parameters. The second type of error function is cross entropy error function. So calculating the cross entropy error function in a neural network, it involves computing the loss between the predicted values, which are almost probabilities, because as I told you, cross entropy error function is used in logistic regression, that is binary classification, where the output is in terms of probability of the class. So calculating the cross entropy error function in a neural network involves computing loss between predicted values, which are often probabilities which are generated by the model, and the true labels, which is your actual output or the target values. So as mentioned earlier, there are two types of common variants of this type of cross entropy, which is binary cross entropy and categorical loss entropy. So where are we going to use this? So binary cross entropy is also known as binary log loss, and they will be used when there are only two classes in the output, which is 0 and 1. So for an example, when you have got your actual output or a true label as y and a predicted output as y cap, both of them being 0 to 1, then there is a formula to calculate the binary log loss, which is this. You know, you are trying to find out loss between the true value of output and predicted value of output. So you have got y log y cap plus 1 minus y. Why this 1 minus y? This is one class y, the second class will be 1 minus y. We are talking on probabilities. Okay. Similarly, log y cap, the other one will be 1 minus y cap, and you are going to add them together. So, this is called as a binary cross entropy loss. The true label is y, range is 0 to 1, predicted output is y cap, range is 0 to 1, okay, and we are here calling that y cap is the predicted probability for class 1. Obviously, the other one will be class 0. Now, to calculate this loss for a batch of samples, suppose you are going for a batch of samples, then you typically average the individual losses, and this is how you calculate a binary log loss, and you try to iterate and find out this loss unless and until you find a minimum loss. Once you get a minimum loss, that is your optimum parameter that you have reached in your neuron model. Now, second type of cross entropy error that we are going to discuss is multi-class log loss or categorical cross entropy. So, as the name suggests, for multi-class classification problems we are going to use this type of loss function. So, given a true label, now when you are using multi-class, then you have to remember we are going to use a one hot encoding. I hope you remember, this is one class, this is second class, this is third class, where the significant position of 1 keeps on changing for every class. I have already explained one hot encoding for you. So, every label is given by a one hot encoded vector, and then given a true label, and then you have got true label represented as y, and then the predicted probabilities are represented as y cap. So, the categorical class entropy can be written as loss of y comma y cap as summation over I is equal to 1 to n minus, and then yi and log y cap y power I, okay. So, that is what you are going to find out the categorical cross entropy as. So, y is a one hot encoded vector representing true class, y cap is a vector of predicted class probabilities for each class, and capital N is the total number of classes. This is how you calculate the categorical cross entropy. So, based on the type of application, choose your type of error, calculate the error, iterate calculations so as to update the parameters, keep on updating, keep on iterating, and find out minimum loss function, and that is where you can say that you have achieved optimization. So, a sample code, how can we use? So, I already told you we are going to use for a feed forward network, a fully connected network, we are going to use a sequential model, and then creating dense layers, fully connected layers. I have given an input function. You can see as an input layer I am choosing activation as a ReLU, and for output function I am going to use sigmoid, because that is how it gives you the range, the classification of binary classification, sorry for this. Now, as you can see, as I compile this particular model, I am going to optimize this model using suitable optimizer. Here I am choosing Adam, and here itself while you are compiling the model, TensorFlow allows you to choose your error. So, here since I am doing binary classification, I am using loss as binary cross entropy. So, that is how you are supposed to select your error function and go towards optimization.